NextGen's FF-ICE execution project focuses on exploring steps to improve future stakeholder collaboration to take another step towards trajectory-based operations. In 2012, ICAO published the FF-ICE document so the aviation community could begin exploring the types of information needed, when the information would be shared, and what should happen with the information when it was received. The concepts explored during this project were refined, demonstrated, and finally recommendations will be submitted back to ICAO. As a component of the ICAO Global ATM concept, FF-ICE defines information requirements for flight planning, flow management, and trajectory management. It aims to be a cornerstone of the performance-based air navigation system. FF-ICE is knowing and using information, but SWIM is another key component to achieving TBO. SWIM provides the conduit for moving the information to the right place at the right time. Ground-to-ground and air-to-ground SWIM are essential components for TBO. Both FF-ICE and SWIM are key enablers for trajectory-based operations. Today, our ATM service providers and our airspace users are not equipped or trained to implement TBO. For TBO, our operations and equipment must be enhanced. Enhanced is the term used to describe an FF-ICE capable airspace user, to include flight operations centers, aircraft, and flight crew. It also applies to our ATM service providers, systems, and operators. With FF-ICE enhancements, real-time communications will provide robust strategic information. Enhanced systems will provide improved operational flexibility, and fully supported time-based trajectories will be a reality. The FF-ICE execution project explored how FAA modernization efforts can support TBO and explores a range of operational and technical solutions to fill in gaps. The key goal is that stakeholders can collaborate and share information on time-based flight trajectories and do so in a strategic manner. In 2016, the FF-ICE program was initiated. The first project was the International Interoperability, Harmonization and Validation, or IIHV. The project focused on FF-ICE elements associated with pre-departure. Immediately following the IIHV project, the FF-ICE execution project was kicked off. 3 activities were conducted, all with a focus on leveraging the efforts of IIHV, while looking to the post-departure or execution phase of flight. The last activity, Demo 2, is the scope of this video. The Global TBO project is slated to kick off in 2020. To explore these concepts, NextGen partnered with other air navigation service providers, industry, and thought leaders from operations and systems domains. To ensure FF-ICE concepts were developed and refined, the team conducted guided discussions and tabletop exercises. They were then shown to the broader community of stakeholders as demonstrations. When feasible, commercially provided systems such as electronic flight bag, flight management systems, and flight operations center tools were used during the demonstration. To get a better look at FF-ICE in action, let's look at some highlights from Demo 2. In this first segment, we will explore one of the scenarios from Demo 2 that highlighted some of the key FF-ICE concepts from the planning phase. We begin as the ANA Flight Operations Center prepares a preliminary flight plan for Flight ANA 6. ANA 6 is scheduled to depart in 6 hours from Narita International Airport, Japan, and fly to Los Angeles International Airport in the United States. In this clip, we will explore some of the FF-ICE enhanced flight planning processes. We begin with an already approved preliminary flight plan for ANA 6. Because the ANA 6 flight plan is published early, the FAA continuously analyzes that flight information via its reevaluation process. This process looks to optimize the NAS while providing airspace users with maximum flexibility through transparency. The re-evaluation process identified and then informed ANA dispatchers that an altitude reservation, ALTREV, is active along the route and conflicts with the current plan. By using the FF-ICE re-evaluation process, previously unknown constraints are made apparent to ATM planners and communicated to airspace users. In this case, the FAA sends a non-concur message to ANA. Now that ANA is aware of the ALTREV, they can exercise an FFICE trial request, where the airspace user can check possible new trajectories to circumvent the constraint. Because it's automated, they receive instantaneous feedback from EASPs that may then be used to request a formal ATC clearance. The operator selects the best route and submits the enhanced trial request and receives concur back from JCAB, and moments later from the FAA. Now that ANA knows the route is viable, they accept the route and submit the enhanced flight plan. While we wait for the EASPs to process the new flight plan, it's important to remember that this scenario showed that the FFICE reevaluation process provides real-time updates to all users. The trial request process allows airspace users to look for the best routes to optimize their fleet, and the enhanced flight planning process provides the entire system with real-time information, which is essential for collaborative decision-making. This is another step towards trajectory-based operations. And we see that ANA just received acceptable from both EASPs. The enhanced systems shown during the ANA scenario include TOPS for JCAB TFM capability, FMS, ATOP, Data Governance Module for SWIM message exchange, and ANA FOC. In the second segment, we will explore the Flight ROU 1950 scenario that demonstrated some of the key FFICE concepts from the execution phase. As ANA 6 continued on its way into Oakland Oceanic Center, the demonstration moved to the other flight, ROU 1950, already en route from Panama City to Toronto at flight level 340. As ROU 1950 approached U.S. airspace, the FAA established a Flow Constrained Area, FCA, and published a reroute advisory for aircraft on Atlantic routes from the Caribbean. The white arrow added here points to the FCA in the left panel of the display. In essence, the FAA identified bad weather and other constraints that impacted traffic flow to include ROU 1950, so they began strategically rerouting aircraft affected. To manage such a significant change in traffic flow, air service providers initiate a reroute advisory or playbook that is specifically designed for that event. In this case, the FAA's reroute advisory is based on the Florida Northeast 3 playbook. Let's see how FFICE can support such an event. After collaborating with the crew, Rouge Dispatch submitted a trial flight plan to the FAA for a trajectory that is aligned with the reroute advisory. The FAA responded back with non-concur, with negotiation horizon error provided as the reason. The negotiation horizon is an FFICE concept explored during this project. It is a dividing line between strategic and tactical negotiations. Remember that FFICE, as explored in this project, is only for strategic purposes. In this case, ROU 1950 needed to plan their trial requests further out along their flight path. To correct it, they created a new trajectory further downstream of the negotiation horizon. After an appropriate revision request was sent to FAA, the FAA responded with acceptable. To close the loop and in accordance with FFICE, the FAA then distributed an agreed trajectory message to NAV Canada, the only downstream EASP. To complete the agreed trajectory process, NAV Canada acknowledged the message as shown on the NAV Canada TFM system. Although not shown in this video, the ROU 1950 scenario continued with the team demonstrating other aspects of the FFICE execution phase, to include the reevaluation process, revision proposals, and the timing between requests and revisions. The enhanced systems shown during the ROU scenario include NFO tool for FOC functions, MTEC for TFMS emulation, NAV Canada TFM, Boeing electronic flight bag, and CPDLC was also shown. This demo showed that using FFICE, airspace users and ATM service providers can agree on strategic changes to a flight's trajectory, even adapting to imbalances and constraints that are thousands of miles downstream. Greater predictability will allow EASPs to more effectively manage the flow of their system's air traffic and will allow airspace users to more efficiently manage their fleet. More information about this demonstration and NextGen's partnerships with JCAB, NAV Canada, and industry can be found at FAA.gov.